Good morning. So I'm going to discuss earthquake processes, what we call the seismic cycle, how earthquakes relate to plate tectonics, and how earthquakes are contributing to shaping the Earth's surface. So the roadmap for the talk, so I will, there's one point blank. So I'm going to remind you the phenomenology of earthquakes, so that will complement what Christophe has been presenting this morning. Then we'll discuss some features that are well explained by plate tectonics. Then we'll discuss some features that are not well explained by plate tectonics, and this is what we're working on today. I will use three case examples from different plate boundaries, and I will talk about the Himalaya. And then I will close with a perspective about modern perspective about earthquake forecasting. So we've known about earthquake for a long time, and first from ground shaking. And for a long time, we knew about earthquake from damages, and starting in the 19th century, we started to be able to record earthquakes. So here it's a simple graph to explain the principle of a seismometer. So a seismometer is basically a pendulum that is going to oscillate as the ground is shaking. And if you imagine that you're drawing a piece of paper and you attach a pen to this pendulum, you're going to measure the displacement of the ground. In reality, we don't do it this way because most of the time the displacement would be very small. We would be talking of a fraction of a millimeter. So we're using electromechanical systems to amplify the ground motion. And it used to be recorded on paper. Nowadays, it's going to be digital. It's on the computer. And the modern instruments are getting smaller and smaller. So this is an example of an instrument that was developed at my former lab in France at the Laboratoire de Détection Géophysique at the CEA. This instrument was a very good quality instrument. It was about this size. And now we have instruments that are the size of a Coca-Cola can, in which you include the electronics to actually record the ground motion. And now you even have the equivalent of that in your iPhones or that fit on a chip. Right? Actually, by the way, there are applications on smartphones, iPhone, that you can use actually to record the ground motion. It can be good for education. So yes, this is typically what. Yes, that's strange. So that's a waveform looks like. You have different phases that seismologists have learned how to recognize. And it used to be that analysts in the lab would pick P waves, S waves coming from the earthquake and use this information to locate the earthquake through the travel time from the source to the stations. We still do that, but we're moving more and more to using modern technique like machine learning. And now you can feed those digital waveforms to an algorithm, and you detect 10 times as many earthquakes as what you can detect with analysts looking at the screen. So this is where this is going. So nowadays we still use seismology, of course, to study earthquake, but we also use other techniques, and Christophe has been talking about GPS. So GPS has been an important source of progress in earthquake science over the last few decades, because not only it provides information on what happens at the time scale of an earthquake, but also at what is happening between earthquake, the slow process of stress buildup on fault. And I will put some focus on that problem in the talk. We also use a lot of remote sensing to study earthquakes, so we can use optical images or radar images. In the talk, I will talk only about optical images to make it simple, but that's going to provide important information on earthquake sources. And we still do field survey, although I won't show a lot about field work in that talk. Modeling, we use modeling to analyze the data, but also to develop dynamic model of the seismic cycle, a little bit like we do weather modeling to forecast the weather. We are on track to use dynamic models to forecast earthquake. We're not quite there, but I will explain that later. So let's look at an example. So this is an earthquake that happened in the Himalaya in 2005, a 7.6 earthquake. You might remember it. And what you see here is measurements that were produced using optical images, so images taken from the spot satellite. Actually, it's from Landsat in that case. And so you are at an elevation about 800 kilometers above the ground, and you compare images that were acquired before and after the earthquake. You register very accurately them to the ground, and then you measure the correlation between those images so that you can measure the ground displacement. And what is plotted here is the amplitude of the north-south component of displacement. So the dark colors are showing displacement going to the south, and the light colors are showing displacement going to the north. And what you see clearly on this image is the discontinuity of displacement. This is the fault trace. That's where the earthquake reached the surface. And the vectors are showing the horizontal component of displacement that resulted from slip on the fault during that earthquake. So that particular earthquake ruptured the ground over a distance of about 85 kilometers. So this kind of information provides you, this kind of data provide you information on the fault, where is it that the earthquake happened, and on the amount of displacement. So in that case, you can see that the Himalayan range were thrust over India by about 5 meters on average during that earthquake. When you combine with seismology, you can say something about the time history of the rupture. So you do modeling of those waveforms that we record with seismometers. And when you do the modeling, you can learn about the kinematics of the rupture. So in that case, this earthquake started at a depth of about 15 kilometers. And then it propagated to the surface with time. And the total duration was about only a minute. Okay? So magnitude 7.6, 1 minute, it killed 85,000 people. Okay, that was quite a heavy death toll. So this information, then we use it to actually inform dynamic model of earthquakes. So why is it that faults sometimes slip in large events like we see here, and sometimes they creep, because there are also faults that just creep gently and don't produce large earthquakes. This has to do with how friction on the fault is evolving during slip. And to illustrate that, I'm going to show you the result from a sophisticated experiment we've done at Caltech. I'm privileged to work at a place where we have access to resources for research. And so here is the experiment with my two preferred assistants, who have grown up quite a bit since I took that video. So this is a spring-on-slider system. So you have bricks here on sandpaper. So there is sandpaper glued to the brick at the bottom, and there is sandpaper on the wood plate here. And here what you have is a rubber band. And as my daughter is going to turn the crank, it's going to stretch the rubber band. And so the stress is going to increase at the contact between the slider and the plate. So basically it's this system that is represented here. So let's look at the video. So you see in that case, the slider doesn't move, and at some point it starts to move. So it has episodic slip. And the reason for this episodic slip, and you see that the house cart was not well built, right? It didn't resist shaking. So, by the way, that's something you can build in your classroom, yeah. So why is it that we have episodic slip? The reason is that the friction that is resisting the pull from the spring is dropping during sliding. So you go from what we call a static friction to a dynamic friction, which is lower than the static friction. So you have acceleration because suddenly you have a force that is not resisting, an excess force that is not resisted by friction at the bottom of the slider, and so the slider can accelerate. Okay? You can, if the sandpaper got worn out, it's going to creep. Okay? And you have materials that would only creep. That's when the dynamic friction is actually higher than the static friction. So, yeah, this is our understanding of how fault friction relates to earthquakes. So the idea is that the stress builds up in the interseismic period and then it drops during earthquake. So if earthquake was as simple as that, we would have a periodic behavior with earthquake repeating regularly with time. So let me introduce a few notions that we use to characterize earthquake. The first is the moment. The moment is the integral of slip on the fault, and it's simply actually the area of the fault multiplied by the average slip, multiplied by the shear modulus, which represents the stiffness of the spring. Okay? So in the case of the Kashmir earthquake, we had about 5 meters of slip on average. The area was 85 kilometers in map view. Down deep, it was of the order of 20 kilometers. So this gives you the area, and you multiply by the elastic properties of the crust to get the moment. So you are probably not used so much to the moment, because generally what we report is the magnitude. The magnitude is the logarithm of the moment with the coefficient, but it's a logarithmic scale that depends on the moment. So this plot was already shown, or some equivalent was shown by Christophe earlier, is the famous Gutenberg-Richter plot, which shows that larger earthquakes are less frequent than smaller earthquakes. And actually, if you look globally, you have 1 magnitude 8 every year, approximately. 1 magnitude 8 or larger every year. You have 10 magnitude 7 or larger. Magnitude 10 or 7 per year. That's about it. And when you go to magnitude 5.5, it's about once a year. Okay, so it's the famous Gutenberg-Richter law. So let's talk now about the global distribution of earthquakes. As Xavier was explaining yesterday, a lot of features that we now understand well in the framework of plate tectonics had been known for a long period of time. And this is particularly true for seismicity. So here I'm going to relate to the work that Montessu de Ballor, Ferdinand Montessu de Ballor, did. He was a military who graduated from École Polytechnique in France, and he got interested. He went to South America and did experience earthquake there, and he got interested in earthquakes. And actually, he contributed quite a few important things. He was featured in BSSA in 1912. He's the one who really understood that earthquakes were related to episodic slip event on faults. And also he produced a map of the distribution of seismicity worldwide. And this is the map that he published in 1911. And already, so the black areas are the area producing earthquakes. So he understood pretty well that there was a ring of active seismicity around the Pacific, so along the coast of southern Northern America, on the other side in Asia. And he understood also that there was seismicity from Northern Africa, southern Spain, all the way to the Himalaya. So these features were relatively well known. And today we understand it relates to plate tectonics, but he had already figured this out. Another thing that we've known for quite a long time is that there are places where the seismicity reach at great depth, and this was discovered independently by Hugo Benioff, who was a professor at Caltech, and Kiyo Wadati, who was in Japan. And they both figure out that seismicity at places can reach to relatively deep depth of the order of 700 kilometers with a deep angle of the zone of seismicity of typically 45 degrees. It was understood already before the plate tectonic revolution that this must be related to the ongoing movement in the deep earth. So seismicity contributed a key element to the discovery of, to proving plate tectonics. And here I'm referring to the observations that were published by Lynn Sykes. So Lynn Sykes observed that seismicity related to fracture zones on the oceanic seafloor. So that was at the time we started to understand the morphology of the oceanic seafloor. So the mid-oceanic ridges had been discovered. So this is actually was produced with GeoMap app, this application that Mathilde was referring to earlier. And people had observed that this mid-oceanic ridge were crisscrossed by fracture zones that you see here very clearly. And so Linsites realized that there were a lot of earthquakes falling on those fracture zones, on that they were associated with horizontal shear. Okay? And so this is a more modern view of the same area. So you can see that the red dots are the earthquakes, and they follow very nicely those fracture zones. What they realized is that, if these fracture zones were faults offsetting these ridges, if these things were passive markers being offset by the fault, this is the sense of shear that you would expect. You would expect seismicity to be active everywhere along the fracture zone, and in that case you would expect what we call right lateral slip of motion. So the area on this side would move to the right with respect to the area on that side. But when he looked at the radiation of seismic wave from those earthquakes, he realized that it was going the other way. And this is a clear proof, actually, that those fracture zones are actually related, are transforming motion from one ridge to the other, and that there is expansion, ocean expanding occurring at those mid-oceanic ridges. And that explains also why the seismicity is confined only to the segments connecting the mid-oceanic ridges. So this is what is explained here. So you have opening of the mid-oceanic ridges, and then the sense of motion is the opposite of what you would expect if you were just offsetting those ridges. So that was a very important observation that really demonstrated C4 spreading being active today, right? Okay, so now if you look at a map of seismicity worldwide, I mean, plate tectonics is really in your face, especially if you also plot velocities measured with GPS. Christophe talked about that earlier today. You really see the plate moving and all the action taking place around the plate boundaries. And there are features that we now understand very well. So alignment with the plate boundaries, distribution with depth. So what has been observed is that when you are close to a mid-oceanic ridge, Mathilde talked about that, the crust is very hot, and you can get only very shallow earthquake, and as you move away from the ridge, the plate gets older, colder, and the seismicity will reach to greater depth. And then at some point when you go to a subduction zone, the oceanic lithosphere gets colder and dense enough that it can sink back into the mantle, and that will drag down the isotherms, and so the cold temperatures can reach to depth large enough to explain the seismicity. So this is relatively well understood now. The Weather-Tibbenioff zone is just places where you actually are advecting down the cold lithosphere, and you can produce earthquakes. Now there are a few features that we don't understand well, and we were hoping we would understand that well, I mean, early on when plate tectonics was discovered, and we don't. The first is that all plate boundaries are not equal in terms of producing earthquakes. Some plate boundaries are producing very large earthquakes. We've had the Tohoku earthquake in Japan, magnitude 9.1, the one in Sumatra that Christophe talked about too, also 9.1. And then you have also large fraction of those plate boundaries which are not producing very large earthquakes. Why is it so? Is it that it's just a matter of time? Or is it that they're creeping and not producing earthquakes? Another thing that we still don't understand so well is why is it that at places the seismicity is distributed throughout continents rather than being localized on well-defined plate boundaries. So I'm going to talk more about those two things. So this is a global map of the largest earthquakes that we know of. And the first point to make is that if you look at the moments released globally by earthquake, 90% of the moment is related to the interface at subduction zones. So we call that megathrust, thrust fault reaching deep across the lithosphere. 90%. So that's these are the zones of high seismic hazard, the megathrust. Yeah, nearly all 8.5 that we know of have occurred along megathrust. But as I said, some have produced very large earthquakes and others haven't. So let's discuss now how the process of stress accumulation and stress release at a subduction zone compare with this simple spring and slider model that I introduced earlier. So here's the spring slider again. So you have the slider. You imagine that you're pushing the lower plate under the upper plate. And let's say that A for a little while is stuck to the lower plate. It's going to move toward the backstop. So you're going to have contraction of the upper plate. So here is a movie, an animation that represents the process. So in reality, what will happen is that the upper plate will also be dragged down because of the motion of the subducting plate here. And then it will pop up at some point where the static friction at the plate interface can't resist anymore the stress at the plate interface. And then eventually it will produce a tsunami. So maybe a word of caution about the word seismic cycle. We say we study the seismic cycle. We don't mean that the earthquakes are periodic. The seismic cycle refers to the process by which an earthquake nucleates, grows, and arrests. We don't mean that it's like the life cycle. We don't mean that earthquakes are all the same and are repeating periodically. So early on, when plate tectonics was formulated, people came up with a few simple ideas about how plate tectonics would help forecast the earthquake. The first idea is that if this model is correct to first order, if you know the date of the previous earthquake, if the previous earthquake was recent, you probably have a small likelihood that it's going to produce a new earthquake. On the opposite side, if you know that this plate interface has been quiet for a long period of time, then the probability that you have a large earthquake is larger. So that was the seismic gap hypothesis. And this hypothesis has failed quite spectacularly. Actually, you're better off by predicting that a gap is going to long last, that it's going to break in the near future. So why is it so? Another implication of that simple model is that the faster the rate, the more frequent should be the earthquake. If you assume that you have the same slip during each earthquake and you're pulling the spring twice faster, you should have twice as many earthquakes. So you would expect the earthquakes to be proportional, the earthquake rate to be proportional to the convergence rate at the subduction zone. And this seems to be approximately correct. The last point, which is actually more important, is that there was hope that we would be able to estimate the maximum magnitude that can happen at a particular plate boundary based on geological properties of that plate boundary. And one idea is that the maximum magnitude should relate to the plate convergence. The plate convergence is going to determine the thermal structure because you are advecting heat. You produce heat also by shear heating. So intuitively, it's a quantity that should correlate with the extent of the seismogenic zone. And the age of the plate should also matter, the age of the oceanic plate that is being subducted, because the older it is, the colder it is. And so early on, Larry Roof and Hiroko Kanamori proposed that there would be a correlation between the age of the seafloor and the convergence rate, that the younger the seafloor, the faster the rate, the larger would be the earthquakes. It was looking like, based on the data we had in the 80s, that was working quite well. now we've had quite a few really large earthquakes happening over the last few decades, and they're populating the whole diagram here. So clearly, this doesn't work. And today, we still don't understand very well what's determining whether a particle plate boundary can produce magnitude 9 or not. So we don't understand well, but we can make measurements of those things. And I'm going to explain that based on this simple diagram. So let's imagine that this is the megathrust, so the plate interface along which this plate is being subducted. And let's assume that the gray area is actually tripping slowly, but the white area is the area that would slip episodically during earthquakes. So if you know that area, if you know the slip rate along the fault, then you can infer what is the moment that should be released by earthquake over a certain period of time. The logic is that when you accumulate the slip event from all those earthquakes, they should match the geological rate at which the plate is being subducted in the upper plate. So m dot here is the rate of moment released by earthquake, so it's the sum of the moment of all the earthquake divided by time. And this would be the shear modulus multiplied by the velocity of the plate multiplied by the area of the seismogenic zone. Okay, so if you can measure the area here, if you can measure the plate velocity, you know it from plate reconstruction. If you can estimate the shear modulus from seismic waves, then you have constraint on the rate at which moment is being released at the plate boundary. So a key element here you can see is the area that is seismogenic. If it shrinks to 0, the plate interface is creeping, no seismic hazard. If it's large, then the seismic hazard is going to be larger. Okay. So let's say that you study the seismic hazard on that whole area, that includes the white and the gray area. What you want to know is the ratio of the part that is seismogenic over the area that you're studying. That's this ratio that you want to know. That's going to be the key element helping constraining the seismic hazard. So let me explain how this works. Let's assume that this area is producing only one kind of earthquake, always the same magnitude, so the same moment, M0. So the frequency, and let's assume that you know the slip rate, V, that you know the area that is seismogenic, A, then you can calculate this quantity M dot. And if you divide M dot by the moment released by each earthquake, what you get is the frequency, so the number of earthquakes per year that you need to get so that that white area is slipping at the long-term geological rate. So you can plot this information on the kind of Gutenberg-Richter plot that we've seen earlier. And this is what you would get. So you do the conversion from moment to magnitude. You take the log, and when you plot that equation here, you get a straight line. So either you have large magnitude that would be very infrequent, and or you get smaller magnitude that would be more frequent. And the slope of that curve is actually 3/2. So in reality, it's a little more complicated than that because we don't have only one kind of earthquake. We have a population of earthquakes. We have smaller and larger ones. So I don't go into the math of that, but the idea is that we have a population of earthquake that is represented by the Gutenberg-Richter distribution, and you can determine what is the maximum magnitude so that the moment released by all these earthquakes, when you take the integral of them, is going to match the long-term slip rate on that portion of the fault that is seismogenic. And that will tell you what is the maximum earthquake. So in reality, you have a lot of possibilities. All these red lines are ending at this same blue line, which is showing the frequency magnitude of the larger earthquakes. So you don't know which one is the right seismicity model. You need the seismicity data, historical earthquakes, or instrumental data that will tell you the frequency of the smaller earthquake, and then you're going to extrapolate to see what is the maximum magnitude and the frequency of that maximum earthquake. That's the logic we're following. So now a key element is the area that is actually seismogenic, this white area. How do we determine that? So we use geodesy for that. So again, I'm showing this animation that you've seen. If the plate interface is fully locked, the island is going to sink down, and you're going to have compression of the forearc of the upper plate. So we measure that with GPS. And based on those measurements, we can determine how much locking there is along the plate interface. So again, if the plate interface is creeping, then there would be no deformation of the upper plate. No deformation at all. If it's fully locked, then that part will be moving at the same rate as the plate is subducting. And as you move away, the rate is going to decrease slowly to 0. And so where it's 0, it means that at depth, it's creeping. So basically from this GPS measurement, you can determine really the extent of the area that is locked and that has to slip during episodic slip event. So I'm showing now a few examples. So let's look at the South America subduction zone off the coast of southern Ecuador here on northern Peru. And here the velocities are showing the ground motion with respect to South America. So you can see that here and here, the upper plate is contracting, is moving towards South America at about the same rate as the Nazca plate is subducting beneath South America. So you can tell that here the plate is clearly locked, and here too. Here in that area of the Piura Peninsula, what you see is that the vectors are much, much smaller. Okay? So the peninsula is not contracting much. So it means that here the plate interface is creeping. So you can do a modeling of that and determine the pattern of locking on the plate interface. And you find that it's dark red in the south and in the north, where the plate interface is locked. And it's white here. There is no stress building up. So here you can argue that this gap, because this place is not known to have produced any large earthquake over history, so it would be called a seismic gap. It's going to probably last for long because there is no stress building up there. So that's why, the one reason the seismic gap hypothesis would not work in that case. Okay? So the message here is that although we don't understand why this plate interface is creeping, we can measure it with GPS. And that's going to be an important information for seismic hazard. So this is one example. Let's look at another example from the subduction zone off the coast of Indonesia, so off the coast of Sumatra, more particularly, which has produced quite a few large earthquakes over the last 20 years. And here again, we're using GPS to measure displacement. So here they are plotted relative to the subducting plate. So, but what you see here is that here, the plate interface must be quite large. You have large arrows. And when you move, when you move close, it's relative to the upper plate. So when you are far away from the plate, you see the convergence between Sumatra and Australia, which is on the order of 5 centimeters per year. And when you get closer to the trench, the arrows are getting smaller and smaller. So this is the indication that the plate interface is locked. Okay? So that area here, in the Mentawai Island, has to be quite locked. In the south, you see these vectors are much larger. So here it's more creeping. So you can do, again, an inversion of those data to determine the pattern of locking of the plate interface, and this is what you get. You find that it's quite locked under the Mentawai Islands, but you have areas where it's not locked so much. Then you can compare with the recent earthquakes that have been experienced over since the Great Sumatra Earthquake of 2004. So we had an 8.6 earthquake in 2005 that ruptured that patch that was locked before. So the locked patches eventually slip in large events in that case. That's a clear proof that the logic works. And then we had another large earthquake in 2007, 8.4, which was followed by another small earthquake, 7.9. And those ones ruptured only a fraction of the area that was locked to the south. So not the whole thing has ruptured. So offshore Padang, you have an area that is locked, that hasn't yet ruptured, and you have about 1 million people living at sea level, basically, within 5 meters from the sea level, while stress is accumulating offshore. That's a quite scary scenario. And so let's summarize what we've seen from this example on the previous one. It looks like at oceanic subduction zone, the pattern of locking on the plate interface is very heterogeneous and can be measured from GPS. And it tells you where stress is building up because of the plate interface being locked. And this is where you expect the large earthquake to occur in the future. Then you can use the logic I introduced earlier to estimate how large should the larger earthquakes be and how frequent, so that those lock patch would slip at the rate they need to slip to explain the subduction of the, in that case, of the Australian plate. And when you do the logic, so let's look only at the larger magnitude here, you find that you need magnitude 9 earthquakes with a written period of a few hundred years to explain maybe 500 years or so. No, 200 years to explain the process. So we haven't had a magnitude 9 earthquake recently in Sumatra. Let's look at the past. A way to look at the past is to look at the historical account, but actually in Sumatra you can do something else. You can use coral reefs that are fringing those islands offshore Sumatra. So this is an image of an island that was uplifted during this 2005 8.6 earthquake. And what you see here is the lagoon. This is the coral reef. So you see that the whole lagoon has now been brought to the surface. And so what is interesting is that these corals that are forming the reef are a particular species, Porites, that grow like pancakes and that are tracking the sea level as they grow. And if you look at that particular sample, you can see that the center of the coral is lower than the rim. So that's an indication that the ground has been subsiding as time was passing during the growth of that coral head. So students working with Kerisi, who was at Caltech and is now in Singapore, have been collecting a lot of these samples to track back in time the motion of the island sinking and going up during the seismic cycle. And from that, you can find that in the past, you've had very large slip events. And these two actually were known from history in 1833 and 1797. There were two large earthquakes between 8.5 and 9. And you can even go back in time and do a modeling like we do of the GPS, and this is what is shown here. So you have the plate interface evolving between 1920 and 700, derived from such data, a collection of those coral heads. And what is shown here is where you have a deficit of slip happening on the plate interface, where the fault is locked. So where it's red, you have stress building up, and it gets blue when there's a large earthquake happening. So, and this is the moment deficit building in the interseismic period. So you have stress building up, and then a large earthquake happens. So you have the possibility to move back in time. And when you look at such data, you realize two things. Is that large earthquakes tend to be clustered, and they don't balance over a short period of time. So we're looking at 200 years, and you will see that at the end of that period, we've had too many earthquakes, because the endpoint will be here, compared to the deficit of slip on the plate interface. So it's a very regular process. So why is it irregular? So this is showing the rupture extent during magnitude 8.5 on larger that occurred during that period of time. So why is it irregular? So the view is that you have places on the plate interface that mostly slip during earthquakes, and places where it's creeping. And the idea is that as stress is building up on those things, if you imagine that you have pins. If you have a lot of those pins along the plate interface, it's going to pin the interface entirely. So the whole area where it's packed is going to be locked in the interseismic period. And then at some point, some of those pins will break, and you will have partial ruptures of that area that was locked, like we've seen during the 2007 earthquake in the Mentawai. And then after that, I didn't talk about that. We can have post-seismic creep around those earthquakes, but I won't cover that. So how do we explain this, or how do we model that? We can develop dynamic models like this one, where you have two patches here that actually have a dynamic friction that is lower than the static friction, so they're going to slip in earthquakes. And the area around those two patches is strengthening, so that it's going to creep only. And if you do a modeling of the seismic cycle of on that system, what you find is that if the two patches are close enough, they're going to talk to each other, they're going to interact. If they're far away, they don't talk to each other. So if they're far away from each other, you have more like a periodic pattern. Each patch will rupture in the same earthquake regularly. When you bring them together, then you start to have interactions. And if you look at the simulation here, you will see that you get smaller and larger earthquakes, you have a complicated pattern. So the more patches you have, the more complicated the system is, it gets eventually chaotic. So the challenge to use such models is actually to constrain the model, to constrain where you have the patches and the friction loads and so on. That's where we're trying to head in the future. Let's talk about the third example here, the Himalaya. So we know that the Himalaya is forming because of the collision between India and Eurasia. India is moving today at a rate of about 4 centimeters per year relative to Eurasia. And we know that from plate tectonic, it's been moving at about that rate, a little faster, as Christophe was explaining earlier, for a certain period of time. And actually, you can, using the spreading of the Indian seafloor, you can actually, I moved too fast with my slides. You can actually describe the time evolution of the motion or the position of India as a function of time. So something like 80 million years ago, based on the opening of the seafloor south of India, we can tell that India was about 3,000 kilometers south of where it is today. So what can we tell about the space between the Himalayan arc and Eurasia? Because you have a very large space here. So if you go in the Himalaya, you walk along the rivers. These rivers are quite steep, and actually they carry interesting pebbles sometimes. And this is one of those pebbles that was collected in the Himalayan river. So these black pebbles are coming down from the highest peak in the Himalaya. And so let's break with caution one of those pebbles, and this is what you find here. You have seashells. Okay, so you have seashells in rocks that are now forming the highest peak in the Himalaya. So this is a clear indication that that space between the Himalaya and Eurasia was at some point oceanic. And actually, we know from geological studies that the latest oceanic material that we can, the youngest oceanic material that we can find in the collision zone is about 50 million years old. Okay? So after 50 million years, all you find is continental. So the view is that prior to 50 million years ago, there was an ocean separating India from Eurasia, and this ocean has been closing with time. Okay, I need to click on the slide, I guess. And starting 50 million years ago, okay, so it looks like the animation is not working, but it doesn't matter. You can find it online. And starting 15 million years ago, you have the continental crust of India, which is lighter than the oceanic seafloor, and which not subduct, entering the collision with the volcanic arc, and that's when you start building the Himalayan Tibet. So here's an animation that explains why it is both similar and different from a subduction zone. The reason it is different from a subduction zone is that the continental crust is not going to subduct, so it's going to be scrapped off from the lower part of the lithosphere, which can subduct. And as time passes, then you accumulate more and more crystal rocks at the surface, and you squeeze that, and you form this kind of accretionary prism. This animation is working. That's good. And so the Himalaya is made of is an accretionary prism that has accumulated with time. This is a simulation. The reference is not here by Serge Malaviel group. Key element is erosion here. You have erosion of the wedge, that in the end you find at the surface rocks that are coming from quite deep in the crust. So now let's look at the seismicity. These are the patches that have produced large earthquakes over the last 2 centuries. And what you find is that you have large gaps, seismic gaps, that haven't produced any large earthquakes over the last few centuries. And then you ask yourself, are these gaps permanent? Are they places where the fault is creeping? And, or is there stress building up there? So again, we're going to use the GPS measurements here, which show a convergence of about 2 centimeters per year across the Himalaya to see what's happening at those gaps. And the result is actually not good news. The red color in the background here is showing the degree of locking of this main thrust along the Himalaya. And you see that it's locked all along the front of the Himalaya of a distance of more than 2,000 kilometers. And in width, it's about 120, 150 kilometers. So it's locked everywhere. So in yellow here, you have the rate of moment deficit building up as a function of time along the Himalayan arc. And in blue, this is what has been released over the last 200 years. There's a large deficit here. So if you use the same logic I introduced earlier to say, well, how large, how frequent needs the largest earthquake be in the Himalaya to balance the moment budget, you find that you need magnitude 9 here with a return period of the order of 1,000 years. So you need millenary earthquakes of magnitude 9 or so in the Himalaya. So the animation is showing the principle of the seismic cycle. So it's very similar to what we've seen for the subduction zone. The plate interface is fully locked. One difference here is that now it's not patchy. You don't have those lock patches and those areas that are creeping. The whole thing is locked, which is actually not so good. So let's talk a little bit. How much time do I have left? Okay, so let's talk briefly about the Gorkha earthquake. You remember the Gorkha earthquake, 2015? Quite a large earthquake, right? This is the rupture area of that earthquake, 7.8. It's a very tiny area compared to the area that is locked, okay? So this kind of earthquake, in terms of explaining the long-term convergence rate across the Himalaya, is not doing much. You need much, much larger earthquake to return along the Himalayan arc. And that's why we did magnitude 9 earthquake. So we're a little concerned about those gaps, especially west of Kathmandu, that haven't produced any large earthquake. At least it's 1505. And because I'm running a little bit out of time, I'm just showing an animation of showing the record of from a security camera in Kathmandu during the Gorkha earthquake. And here you're going to see the ground motion measured at one of our GPS stations in Kathmandu. So the earthquake just started, and you see that the ground is moving south by nearly 2 meters, and then it starts oscillating back and forth. These people are about 10 kilometers above a magnitude 7.8. In fact, this is very gentle shaking compared to what would have been expected. It's not very abrupt ground shaking. It's large displacement, 2 meters, but it occurred over a relatively long time of the order of 10 seconds. And then on top you have a resonance of the Kathmandu basin because the city was built over a basin. So 2 things that we learned from our records that I won't go into the details today is that there was not much ground shaking in Kathmandu, and Kathmandu was safe because the source of high frequencies damaging waves were quite far north of the basin. Also, there was large slip beneath the basin. And then we can use the GPS records to actually produce a model of the rupture during the earthquake. So what you're going to look at here is the time evolution of the slip rate on the fault as a function of time. And the color scale goes up to about 1 meter per second. So this is what's happening at depth on the plate interface. So it starts 75 kilometers away from Kathmandu. And you see a pulse propagating toward Kathmandu. It takes about 40 seconds for the pulse to reach Kathmandu. That's why actually early warning is possible. It takes time. Once the earthquake has started, it takes time for the rupture to reach Kathmandu. So we're developing models to try to reproduce this kind of dynamics. And I'm going to show, oh yes, I'm showing that. This is the ground shaking resulting from that model. Now we're looking at the ground displacement, not the slip on the plate interface. You see the waves interacting with the basin in particular. So in this model, there's the Kathmandu basin, and you're going to see the energy of the seismic waves being trapped into the basin and resonating. And that explains the rotational motion that we've seen in that GPS record that was tied to the security camera. You see the shaking of Kathmandu. It lasts for about a minute, and it moves back and forth by about a meter, okay, with a period of 5 seconds. This is what destroyed the really tall buildings, actually, in Kathmandu. The small buildings were not destroyed because they can move back and forth by a meter with a period of 5 seconds. That's not damaging. So here's is an example of a dynamic simulation that was tried to reproduce the Gorkha earthquake. I'm not going to tell any detail about that. The message is that we can now develop dynamic models that reproduce things like the Gorkha earthquake. The future is to use such dynamic models to try to understand how the smaller earthquake, like Gorkha, relate to the really large earthquake that needs to happen once in a while. So here is one earthquake that failed to rupture the whole patch that was locked. The black area was locked before the earthquake, and it has all the characteristics of Gorkha. And now you're looking at the next event. So the Gorkha has happened. It has loaded the plate interface outside because it transfers stress to the area that haven't ruptured. And next, another earthquake will start just like Gorkha. But because the stress level has increased over the locked patch, then this earthquake is able to actually rupture the whole thing. And this is the kind of earthquake that should happen every 1,000 years or so. Okay, so time to conclude. Seismic gaps. So why is it that the seismic gap hypothesis doesn't work? Is that some gaps are actually places where the seismic hazard is not high because they're just creeping. Another reason is that large earthquakes tend to occur in clusters. So that they might last much longer than you would expect if you were assuming that the earthquake would happen, regularly in time. A positive message is that with GPS in particular, it's possible to measure where stress is building up on fault on spot areas of stress buildup, which are areas of higher seismic hazard. You can then use the moment budget approach I introduced to say about where the future earthquake might happen, how large, how frequently they might happen. And I am hopeful that with dynamic models, we might be able to make progress in terms of forecasting earthquake. And when I say forecasting, I don't mean predicting. Forecasting is it's evaluating the probability of an earthquake of a certain magnitude or larger than a certain magnitude over a certain period of time in a certain area. And this is what is really useful for seismic hazard to build better buildings and so on. So I'm going to conclude there. All the animation and graphic I've shown today are available on my webpage or the webpage of the Tectonics Observatory at Caltech. Thank you.